our final section of the day. We've had lots of beautiful talks today, and we're all very excited to have Danny here with college. We'll be talking about the stability of the positive mass theorem. Yeah.
All right, thank you. Everyone can hear me, I guess. Make sure, double check the sound. So we've had a long day. I want to unmute this one, right? Okay. So feel free to stop me and ask questions. I don't have too tight of an agenda here, I don't think. So I want to talk about stability of the positive mass theorem today. And so let me just first start off by reminding people about what the positive mass theorem says. This was working 5 seconds ago. Oh, well, I'll just stand here because I'm not on video anyway. Okay, so first let me just state what I'll call the non-negative mass theorem. And I'm only going to deal with the Riemannian version of this theorem. So in some sense, this whole talk is really about scalar curvature, although of course there are relations to general relativity. But this is really kind of a Riemannian talk here. So the Riemannian non-negative mass theorem says that if you have a complete asymptotically flat Riemannian manifold with non-negative scalar curvature, then the ADM mass is greater than or equal to 0. So I'll denote scalar curvature with this capital R. And later on, I'll give a precise definition of what I mean by asymptotically flat. And I won't bother to define the ADM mass because it's not terribly important. The exact definition is not terribly important for what I'm going to say. Okay, so this is a famous theorem, of course. It was proved in dimension 3 by Shane and Yao using minimal surfaces. They were able to generalize it to higher dimensions a little later. And they have an argument for all dimensions as well. There was another famous proof by Witten for spin manifolds. But also in the sort of, I guess I want to say recent, it's not really recent, but compared to 1981, I guess, there are more proofs available in the 3-dimensional case. So the first of these is the inverse mean curvature flow of Huisken and Ilmanen. And that actually proves something more general called the Riemannian-Penrose inequality, but I'm not going to talk about that today. There's a Ricci flow proof due to Yu Li. And there are now a couple proofs that use harmonic functions. So the first is the one that I'm going to talk about the most today. It's by Bray, Kazaras, Khuri, and Stern. And it involves harmonic functions that are asymptotically linear. And that one should be compared mostly with the Witten proof. So if you're familiar with the Witten proof, it has a similar flavor to that. And more recently, there's been a proof by Agostiniani, Mazzieri, and Aronzio. And that one uses a Green's function type of argument. And it looks at level sets of that function. And so in some sense, that one actually kind of has a flavor that's more like the inverse mean curvature flow proof. Anyway, so there's been some interesting activity. There's this old theorem, and actually I listed a bunch of different proofs, and they're all very different. So I think it actually goes to show how fundamental this idea is, that there are actually many roads to proving it, and the relationships between them are actually kind of difficult to understand. Okay, so PMT rigidity. So I mentioned the non-negative mass theorem said that the mass is non-negative, which I think, just to be, a little more precise with language. So now I'm going to talk about how do you know that the mass is actually positive? So that's all called the PMT. So again, you have a complete asymptotically flat Riemannian manifold, non-negative scalar curvature. But now I'm going to say not only do you know that it's non-negative, I actually know it's positive unless it's isometric to Euclidean space. So Euclidean space is an obvious example where the mass is 0. And the point is that's really the only one. Okay. So when Shane Yao gave their original proof, they proved that what I called the non-negative mass theorem on the previous slide actually implies the positive mass theorem. And it doesn't actually use the proof. So the reason why they had to do this is because their proof of the non-negative mass theorem it's actually a proof by contradiction. So it doesn't actually say anything about the actual cases of non-negativity. So they have a separate argument that if you know non-negativity, then you can prove the positivity. And so, but that's very different from all the other proofs that I mentioned. So the other proofs, since they are not proofs by contradiction, right, they actually somewhat more directly show non-negativity. So you can analyze what happens in that proof at like the edge case of equality. And in those edge cases, then you can actually get a separate proof of the positivity. So instead of referring to this in terms of positivity, I'm going to rephrase this as a rigidity statement. And so that's the point of view that I want to take for the rest of this talk, which is, so this is just a restatement of the theorem at the top. It's nothing new. It's just saying it differently. That if I have a complete asymptotically flat manifold, non-negative scalar curvature, and zero mass, then I can prove that, or one can prove that it's isometric to Euclidean space, right? So that's a rigidity theorem. I have some assumptions. It implies it's isometric to one very specific thing. And so whenever you have a rigidity theorem, you can at least start to ask the question of stability, which is I have these requirements. What if I loosen them a little bit? What does that tell me? So the way that I'm going to phrase this is the following. If I have a sequence of manifolds that satisfy those hypotheses, in other words, asymptotically flat, non-negative scalar curvature, but I don't know that the mass is zero. I only know that the mass is converging to zero. So the mass is getting smaller and smaller. Must it be the case that this space has to converge to Euclidean space in some sense? So I wrote here in parentheses suitably normalized because, right, mass actually has units of well, in 3 dimensions, units of length. And so it makes sense that you need to sort of have some kind of normalization for this to have it be sensible. But you can at least ask this question, is it going to converge? And so for a long time, the reason why this question wasn't asked like earlier is that it kind of is obviously no in most of the senses that you want to think about it. So, so quick complications with this stability question are, okay, so first and foremost is that the existence of minimal surfaces, right, which in this Riemannian case correspond to apparent horizons. That complicates the stability question because we kind of understand that complicated geometry can sort of hide behind a minimal surface in a non-negative scalar curvature space. In other words, you can have a really small, tiny minimal surface, and yet on the other side of that minimal surface, there could be very large geometry which you have no control over. So for that reason, there's no sense in which the stuff behind that horizon is close to Euclidean. Okay, so that's one major complication. Sorry, so but there's kind of a way that you could talk about how to deal with it, which is that, well, maybe the right way to think about the study of asymptotically flat manifolds with non-negative scalar curvature is that you should really only think about what's happening outside the horizon anyway. Because when I say study, I mean specifically study properties of the mass and how the mass relates to the geometry of the entire manifold. Well, if you're thinking about that relationship, it's never going to relate to the geometry past the horizon. So for that reason, it's natural to restrict attention to the region, and I'm using AF here for asymptotically flat. You really only want to look at the region that's outside the outermost minimal surface, or you might just restrict your attention to manifolds that don't have minimal surfaces in them. Although the former, I guess, is more ideal. Okay, but even still, there are still more complications besides a minimal surface, because even without a minimal surface, it's still possible to have arbitrarily long and thin, I guess what we'll call gravity wells, while still having very small mass. And that observation shows that not only can you not only should you not expect convergence in any kind of smooth sense, but actually, like, even the most common kind of geometric convergence that's a little loose is Gromov-Hausdorff, and Gromov-Hausdorff convergence also is not going to happen. And so let me illustrate that with a picture. Okay, so I have 4 examples of really simple spaces. going downward, I'm looking at a sequence whose mass is going to 0. So the first picture is kind of like what we hope was going to happen, right? So the mass is getting smaller, and it's sort of converging to Euclidean. It's getting flat. Okay, that's good. We're happy with that. The second picture, I've put a little minimal surface there at the bottom. Okay, in this picture, the mass is going to 0. The minimal surface is also getting smaller and smaller, and even though I'm going to be missing that point at the origin, it still kind of makes sense that that looks like it's converging to Euclidean space as well. So that's not a problem either, as long as you think about, okay, just look at the part outside the minimal surface. Okay, but now the third picture, that's starting to have some issues. So in the third picture, I still have a small minimal surface, and the size of that minimal surface is still going to 0, but actually the minimal surface is somehow going farther and farther away, in the sense that like it's at the bottom of a long, almost cylindrical piece. Okay, so that's something that can happen. And the fourth picture, there's no minimal surface at all, but it's still the case that we're developing this kind of long spike, and that's the thing that I call the gravity well, in quotes. So the point is, the two pictures on the right, you can have these examples where the mass goes to 0, but as you can see very clearly, if you're thinking in terms of distances, the distances involved are not converging to the corresponding Euclidean distances in the bottom of the picture, right? So just as a brief reminder, without getting into the definitions, Gromov-Hausdorff convergence is a convergence that respects distance. Okay, so we have situations that clearly do not respect distance. Any questions? All right, so let's move on. So one way of sort of getting around this issue is maybe to introduce a different kind of distance, not Gromov-Hausdorff distance, but in this case, we'll talk about Sormani-Wenger distance. So just in Euclidean, just in RM, there's this concept of the flat distance. So the flat distance between two oriented n submanifolds T and S is defined by this. So I'm being a little loose, and I don't want to write down all the details, but basically you look at all possible A and B such that the difference of T minus S is equal to A plus the boundary of B. So in this case, A is the same dimension, n dimensional, and B is one dimension larger. Okay, and then you take the sizes of A and B, that's what the absolute values here are supposed to represent, size of A plus the size of B, volume of A plus volume of B, and then look at the smallest possible quantity you can get for this. So if you've seen this before, it's old news, but if you haven't, let me just describe the simplest situation where, just say T and S are just hypersurfaces without boundary. Then this is just asking, what's the smallest volume you can do? What's the smallest volume that will fill the space between those two submanifolds, right? So I have submanifold here, submanifold here, and then just fill in between it. So the idea is the two submanifolds are close if they're close in this sense, that the space between them can be filled by something small. That something small would be the B. Okay, in that case, the A is just empty, so it's easier to think about. Anyway, so that's the flat distance, which is very, very, very heavily studied in geometric measure theory. And more generally, it works not just for submanifolds, but for objects called integral currents. Okay, so they're weak objects, which for the purposes of this talk, I don't really need to talk about at all. But what I will say is that important development was that Ambrosi and Kirchheim, they developed a theory of integral currents in metric spaces. So the typical setting for these guys is in RM, but you can actually define them in an arbitrary metric space. And then once you have them defined in a metric space, it's possible to define the flat distance. Okay, so there is a notion of flat distance in metric spaces. And once you have a notion of distance in a metric space, then that allowed Sormani and Wenger to invent an intrinsic version of the flat distance. And it's in very direct analogy to the way Gromov-Hausdorff distance is an intrinsic version of Hausdorff distance. So Hausdorff distance, that's just distance between sets in a metric space that we learn about in analysis, basic analysis class. but then the intrinsic version is defined in the way that I'm going to describe now, which is if you want to take the Sormani-Wenger distance between two Riemannian manifolds, okay, then what you do is you isometrically embed them into a common metric space Z, compute the flat distance there, and then whatever that flat distance is there is an upper bound for the Sormani-Wenger distance. So the Sormani-Wenger distance, you just take the inf over all possible embeddings into all possible metric spaces. This is very abstractly defined, but you can find upper bounds in a very concrete way as long as you can find these embeddings. The main stumbling point for us usually is that when we say isometric embedding, we mean in the sense of metric spaces, not in the sense of Riemannian geometry. So that's what actually makes it quite difficult to work with this distance, is that you have to always be working in terms of metric geometry, which is tricky. Okay, so I'm just introducing this because now I want to talk about how I can state stability in terms of Sormani-Wenger distance. So, well, I don't know, this could have been on the last slide, I guess. So flat convergence was really useful in the study of minimal submanifolds. And the reason sort of why intuitively is that if you think about like the direct method for finding minimal things, then there's kind of like these little pieces that you want to ignore, and flat convergence will let you ignore them. So the similar idea is that the hope is that Sormani-Wenger convergence will prove useful for lower bounds on scalar curvature, because although the gravity wells that I talked about, they don't vanish in the Gromov-Hausdorff sense, but they do vanish in this Sormani-Wenger sense, at least intuitively they should. So this at least is a possible topology in which the stability that I want could be true. So as a base of proof of concept, Sormani and I proved the following theorem. I guess back in 2014, we just looked at spherically symmetric examples. So just look at spherically symmetric asymptotically flat manifolds, non-negative scalar curvature. And again, they either have no interior minimal hypersurfaces or it has a minimal boundary, right? That's the outermost kind of assumption. So I'm just naming the script M as like the class of such objects, okay? And just together with a distinguished point lying on a symmetric sphere of fixed area. So this is kind of the similar, this is where I'm sort of fixing a scale more or less. Okay, so it's a statement, it's a pointed manifold. Then the result is that if you have a sequence of these symmetric guys whose mass is going to 0, then it actually does do exactly what I want. It converges to Euclidean space in what's called the pointed Sormani-Wenger topology. Pointed just means, you fix a ball of a certain size and that ball converges. Okay. So, I mean, in some sense, I mean, it's partly easy to prove because the spherically symmetric case, of course, we know everything about it. It's just like analyze it with ODEs. So we can understand those examples very easily. The only work comes in basically is in making it fit with the Sormani-Wenger distance. Like we have to explicitly compute distances in Sormani-Wenger. And we have a similar result for the Penrose inequality as well, which I didn't mention the Penrose inequality, so I won't get into that. But I will say it's a little bit different. You want to show that something converges to short shield, but you don't actually get short shield. It's short shield potentially plus a little piece of cylinder, which makes sense because those are kind of in the limit of objects that have minimal boundary. Anyway, so that's kind of the starting point for this story, which led us to make a conjecture. And so before I say the conjecture, now I'll give the technical definition that I didn't want to bother with, but I'm sure most of you are familiar with what it means to be asymptotically flat. So I'm going to be a little more specific about it, though. I'm going to say QB asymptotically flat. So Q is going to be bigger than n-2/2. It's going to refer to the decay rate of the flatness. Okay. So asymptotically flat means it's a compact set K, such that after you take out that compact set, you're diffeomorphic to just trivial R3 minus a ball. Oops, that should be an Rn minus a ball. Sorry. Okay, so And in the coordinate chart, it just says that the metric looks like Euclidean. That's the delta ij up to order x to the minus k minus q. So the difference between the metric and Euclidean decays like x to the minus q. Its first derivative decays 1 order faster, and its second derivative decays 2 orders faster. Okay, so q is the decay rate. B is just going to be a number which I can sort of use to specify, like, okay, how far off is it? So it's basically going to be like a uniform parameter for how asymptotically flat it is, I guess. Okay, and also on top of that, I require the scalar curvature to be integrable. So with these assumptions, these assumptions allow one to both define the ADM mass, which I'm not going to do, but with this definition, the ADM mass is well defined, and these are the assumptions that are needed for the positive mass theorem to hold. Okay. Okay, so now, oops. With this, so in the same paper, we made this conjecture. The way I'm stating here is kind of an updated version of the conjecture. So this is a way of stating, which I think is at least, could plausibly be true. I don't know. So, and I did it again. I have an R3, that should be Rn. So, so now I'm going to take a space of QB asymptotically flat n-manifolds. So in other words, the B is saying the family I'm looking at is uniformly asymptotically flat. So that's the sense in which I'm fixing a scale. Okay, so it's uniformly asymptotically flat. I'm going to pick a point that's outlying in the coordinate chart. Okay, then again, I want to say that if this sequence has mass going to 0, then it converges to Euclidean in the pointed Sormani-Wenger topology. Okay, so this would be kind of like, this is the grand conjecture, and we really don't know quite what we'd need to do to prove it, but I just want to emphasize that, right, it's stability for the positive mass theorem rigidity. So it's a much stronger statement than positive mass theorem rigidity, right? So it needs to somehow, the tools that would go into proving such a thing have to be stronger than the tools that would be used to prove PMT rigidity. Okay, and for that reason, again, the classic Shan-Yao proof is a little hard to use because remember, it's a proof by contradiction. So if we're going to do this, then probably we want something that's more quantitative, like the other proofs that I mentioned. Okay, so let me say a little bit about progress on this conjecture. So first, but before I get into the what's known, I guess, is I want to say the Sormani-Wenger topology. One reason why we state the conjecture in this way is that it has a lot of good properties and it's a plausible candidate. In other words, it's at least possible that the conjecture is true. And remember, it was motivated by this idea that the Sormani-Wenger distance sort of doesn't see the gravity wells, but it also has good well-known properties that were established by Sormani and Wenger. Plus, including Wenger has a compactness theorem for these objects. So that's one reason why we like it. But I want to emphasize that replacing the topology with any reasonable topology on Riemannian manifolds, or anything even that's, I think, could be arguably geometric. It doesn't even have to be a topology, but something that involves you using the mass to bound geometric properties of the object. I think that would be interesting. So a good example would be somewhat recently, there's been the development of something called DP convergence. That was by Man-Chun Lee, Aaron Neighbor, and Robin Neumeyer. That would be a great example of something that you could do. Okay, so that's that. But let me say some results that have been proved that are in the direction of the conjecture. So spherically symmetric is very narrow. So the next case that we really looked at was graphical hypersurfaces of Euclidean space. And so Lan Xuan Huang and I proved a result basically saying that you more or less, under some assumptions, you get flat convergence in Rn, right? Because it's in Euclidean space. And then together with Sormani, we improved that so that it wasn't just flat convergence, it was actually this intrinsic flat convergence of Sormani-Wenger convergence. Unfortunately, our proof actually had a gap, but it was able to be fixed. There was some work of Brian Allen and Raquel Perales who developed some tools that could be used to get around it. And then Juan, myself, and Raquel Perales, we used those tools to fix the problem. So the main result of the paper I mentioned is actually still holds. Okay. So there's also a quasi-local version of this graphical hypersurfaces result. So our statement is about the mass going to 0. So their statement is about the Brown-York mass going to 0. And so that was done by Ala'i, Cabrera-Pacheco, and McCormick. They proved that the Brown-York mass going to 0, then you get some convergence to Euclidean. Again, there's some technical assumptions as well, but that's the basic idea. Brian Allen first started looking at, as I said, you need a proof of positive mass theorem to make these things work. So I should say the reason why we were able to prove these cases in the graphical hypersurface case is because there's a particularly simple proof of the PMT in that case. And so that's very powerful. We were able to get a lot of mileage out of it. So using the inverse mean curvature flow approach, Brian Allen proved a theorem about L2 convergence of the metric. But I should say that that theorem requires a lot of assumptions about what you start with. So it's not totally general. Geometrostatic spaces, Sormani and Stavrov. Axisymmetric spaces were studied by Bryden. He showed that there's a W1P convergence for those spaces. And then Bryden, Khuri, and Sormani also worked on the spherically symmetric initial data sets. So everything else I'm going to say today is just about Riemannian manifolds, but that was one result about initial data sets. But then there's also asymptotically hyperbolic versions of some of these theorems. So for example, the theorem I had on the previous couple slides ago for symmetric spaces, there's a hyperbolic version of that was done by Sakovich and Sormani. And Brian Allen generalized his theorem to the hyperbolic setting. And Armando Cabrera-Pacheco generalized our graphical hypersurfaces theorem also to the asymptotically hyperbolic setting. So there's been a lot of different kind of works on this. I'm going a little fast. I don't know. I got like a ton of time. Yeah, I'm like burning through this talk. But anyway, are there any questions? I feel like I need to be slowed down. When I gave that CMSA member seminar talk, there were so many questions, so it's like totally different. That's okay. Oh, the hyperbolic state? Oh yeah, no. So the gap was only when we tried to move to we went from the flat to intrinsic flat. That was the problem. So this theorem in the hyperbolic one, they only did the flat convergence. They didn't do the intrinsic flat convergence. But you think it works? Oh, probably. I don't know. I haven't actually thought about it. Yeah, probably. Well, probably. It could be tricky. It could be quite tricky because again, these things are very yeah. Because so this is why I say it's tricky. I guess proving that something converges to something like a Euclidean ball in the intrinsic flat sense or in the Sormani-Wenger sense seems a lot easier than showing that something converges to a hyperbolic ball, which is what you'd have to do for this one. But yeah, no, I never really thought. That's a good question. Yeah. So one thing I'll say about all of these things is that they all deal with somewhat special cases, which is unfortunate, but it's also not surprising because the general statement, as I said, I think it covers a lot and it's very difficult. So, but all the special cases, as I said, they kind of involve the fact that in special cases, you have more precise or more powerful versions of the proof of the PMT, right? So that's why special cases you can expect to get a better stability result. So the real question is, how do you go to something that's quite more general? That's the hard part. And so here's an example of that sort of, which is the main result that I want to talk about today, which is PNT stability with a Ricci lower bound. So this is joint work with Dimitri Kazaras and Marcus Khuri, both of whom are giving talks in this conference later this week on other topics. So I'm carrying this one here. So this is the statement. This is actually in 3 dimensions. So the 3's here are correct. So in 3 dimensions, if you look at the class of complete QB asymptotically flat 3 manifolds with non-negative scalar curvature, okay. So remember, Q just means they all have this. There's a uniform decay rate Q, but that's not so surprising, and a uniform asymptotic flatness B. Again, B doesn't have to be small, but it does have to be uniform. So in other words, we're not going to go have everything staying within kind of a bounded amount, okay? But then I'm also, in addition to that, I'm going to take this kappa. Sorry, I'm not going in order. I want an empty boundary, and I want vanishing second homology, and Ricci curvature bounded below by minus kappa. So this is the big assumption here, is that I want a lower Ricci bound of some sort, okay? And I'll say the vanishing second homology you should think of as it's like a slightly weaker version of saying no interior minimal surfaces. So it's a topological condition, but it's similar in nature to that. Okay. And again, I'm going to take a distinguished point lying in the coordinate chart. So that's again, it's a pointed manifold. So then the result here is that if I have a sequence of these and their masses converge to 0, then the sequence converges to Euclidean space in the pointed Gromov-Hausdorff topology. Okay. So in the first part of the talk, I explained why the general theorem can't possibly be true with Gromov-Hausdorff topology, but now I'm giving you a result that does have Gromov-Hausdorff topology. And as you might guess, the reason why is because I have a Ricci curvature bound. Okay. So for those who study Ricci curvature, this is not surprising because right, Ricci curvature kind of plays nicely with Gromov-Hausdorff topology. There's a lot of classical results that have that kind of flavor. Okay. So on the one hand, I want to say that you know, in contrast to a lot of the other theorems I put on the previous slide, I feel like this one is not. It's a restricted situation, but not a special case. It's very, it covers a lot of grounds. It's very general, and so in that sense, I think it's something that we're proud of. But I do want to say that in terms of attacking the full problem, it's still very far away in the sense that, Ricci curvature bounded below by minus kappa, you're not really thinking about it like, oh, that doesn't seem so bad, except that, the cases that we really care about and the cases that we really want to understand do have Ricci curvature going to negative infinity. So for example, if you just take short shield, take the mass go to 0, then near the horizon, the Ricci curvature actually does go to minus infinity. Okay. And similarly with those little gravity wells, the whole point is those gravity wells, essentially as a consequence of this theorem, you can say like they pretty much have to have Ricci going to minus infinity. Okay. So I feel like the phenomena that we most desperately want to understand is not covered by this theorem, but this theorem does kind of cover everything else, right? So if you just put this lower bound on Ricci curvature, then everything's okay. You get basically the best theorem you could hope for, I think, under these hypotheses. Okay, and unfortunately, it's not the case that Gromov-Hausdorff topology it's not actually like stronger than Sormani-Wenger topology, but under the assumption of the Ricci curvature bound, it's sort of like that. So we didn't actually think about whether this converges in Sormani-Wenger, but it probably does. Okay, so the proof is based on the following inequality from Bray, Kazaras, Khuri, and Stern. And that's this one. So what does it say? It says that if I have any harmonic function that's asymptotic to the coordinate function xi, so it's 3 dimensions, so there's just 3 coordinate functions, x1, x2, x3. you can find a harmonic function because of the asymptotic flatness, right? You can just solve essentially like with a boundary condition more or less, right? That you can find harmonic functions that are asymptotic to those linear coordinate functions. And for every single one of those functions, we're going to have this inequality. So every single one, there's only 3 of them, but we have this inequality, okay? And so this inequality is actually the reason why I said it's not important for me to write down the definition of ADM mass, because I don't care what the definition is from the point of view of proving this theorem. I only care that the ADM mass satisfies this inequality, okay? And if you're familiar with Witten's proof of the positive mass theorem, then this has a similar flavor, okay? So what it's saying is we have a term in the front, which is manifestly non-negative. It's the Hessian squared divided by the norm of the gradient. And then the second term is where the scalar curvature comes in. Yeah.
There is a hand up.
Yeah, sure. Great.
Hey, Dan.
Hey.
So yeah, so this formula is reminiscent of Witten's formula. So can you just say quickly in words why this is so much more useful for this than the spinorial condition?
Oh,
the
that's
spinorial formula.
That's an excellent question. So so one possible answer to it is maybe so the question is there's a similar formula for the mass in terms of the Dirac spinner, right?
Yeah.
So there's a spinner that solves d psi equals 0, and you get a kind of a similar-ish formula. The question is why can't you use that? And so, well, one answer is, well, maybe you could if you were smarter than we are. But I would say that for me, the thing is, the spinner just seems less intuitive for thinking about kind of geometry than a harmonic function.
Yeah.
So it's entirely possible. Maybe there is a good proof of this that just uses
Right.
Which would be great because then it would work for all spin manifolds potentially, rather than just 3 manifolds.
Sure. Okay.
Right,
Thanks.
Yeah. So this formula I wrote down only works for 3 manifolds, and also it only works for 3 manifolds with vanishing second homology, which is the reason why I had to have that condition there. Okay, but yeah. So we'll see. Okay, so I'll give you a quick intuition for why. Right, these harmonic functions, right? When we go to Euclidean space, we know exactly what they are. They're just the flat coordinate functions in harmonic space. So the idea is that we have this space and we already have an idea about how to compare our space to Euclidean space. The u sub i's, u1, u2, u3, we want those to be our coordinate functions such that in those coordinates, our metric becomes close to flat. That's the intuition behind this. And so that's easy to see. Of course, you can do something similar with I guess spinners, because there's some relationship between spinners and vectors, of course. So you could try something similar. So potentially there's something there. But anyway, so that's what we're going to do. I should say this formula by Bray, Kazaras, Khuri, and Stern is based on work of Daniel Stern alone, who had a similar formula just for mainly applied to compact 3 manifolds. So they kind of just generalized that to asymptotically flat spaces to get this formula. Right. Okay. Yeah, Dimitri has a helpful comment in the chat as well. Okay, so let me just quickly outline the proof. Yeah, so I think Dimitri spelled out something that I said less explicitly, right? That it actually tells you, part of Gromov-Hausdorff convergence is like there's a map from your space into the target space, and so that's this is giving us the map that we want, so we know what map we want to use. Okay, so I'll spend the rest of the time just outlining the proof. I'll try not to be too technical, because there's actually quite a lot of details in this proof, but let me do my best to give a bit of an overview on how it works. So the first thing is we use this bound together with the Cheng-Yao gradient estimate and the bounds on Ricci and asymptotics to obtain the following bounds. So, so first I'll say the Cheng-Yao gradient estimate requires a lower Ricci curvature bound. So right off the bat, everything we're saying really uses the Ricci, which is unfortunate because again, the idea is hopefully you could adapt these ideas to get rid of the Ricci assumption, but it's being used in a very essential way throughout this proof. Okay, so the first is just that the gradient of ui minus ddxi is less than c times x to the minus q. Okay. In other words, it decays like minus q. But so first, let me just say is that this is just an immediate. If the decay is an immediate consequence of asymptotic flatness, the non-trivial thing is I want the c to not depend on where I am in the family, right? So the capital C I have here, I want that to only depend on, right, the Q, B, kappa, right? The uniform family of spaces I'm looking at. I want a uniform bound. So that's what's non-trivial about this. So it's immediate that you get the decay, but I want a uniform decay. Okay. So remember, U is asymptotic to xi, so it's not surprising that the gradient is asymptotic to ddxi. So that part is the first step. And then using that, we can also prove that there is a sup bound on the gradient of U. Okay, and again, the point is the sup bound does not depend, it only depends on Q, B, kappa. It only depends on the family, not on individual elements of the space. Okay, so so that's that. And then using this, I immediately get the following. I get a bound on the L2 Hessian of ui. Okay, so you can see this now just follows from the gradient bound and the inequality I have at the top of the page, right? Because I'm assuming r is greater than or equal to 0, and if you have an upper bound on the Hessian, then that troublesome denominator you can just ignore, and you actually get a bound on the L2 Hessian. So from here, this question is, how can we use the bound on the L2 Hessian, which is going to be as small as we want, right? Because the M of G is the thing we're going to take to be small. And I want to use that to prove the Gromov-Hausdorff convergence. Okay, so let me give a vague idea of what's going on. Again, so remember, I want to think of the U1, U2, U3 as like coordinate functions that I hope are going to be like make my metric look like the Euclidean metric. So the idea is to use the almost orthonormality of the infinity. So you know that those, because the first estimate I have there tells me that the gradients are just like ddxi. ddxi, it's asymptotically flat. Those are pretty close to being orthonormal at infinity. So these gradients are also pretty close to being orthonormal at infinity. And then I want to integrate inwards using the smallness of their Hessian to get almost orthonormality in the compact region, basically far away from infinity. Okay, so that's the basic idea. That's the strategy, is the Hessian is small. I understand the gradients out in infinity. I can just integrate them inwards to understand them everywhere. Okay, so there's an obvious problem that's not going to cut it, because I only have L2 smallness of the Hessian. Okay, L2 smallness is not enough to integrate along any geodesic. Okay, so that's the problem. So luckily, and this is kind of the starting point for the project, is that we know that, you know, there's thankfully this solution in this work of Chigger and Kolding. They have something called the segment inequality, and they used it to prove their almost splitting theorem in 1996. Okay, so that was a theorem about Ricci curvature, right? So there's the Ricci curvature splitting theorem. The almost splitting theorem is, you know, you don't have a line, you have like an almost line. So you almost split. So it's not important exactly the statement, but the point is that they face the same issues that we face, and so we can just copy what they did, and that's what we did to do this part. So the segment inequality tells us that this can be done modulo small perturbations of points. So and the segment inequality, again, I'll say, so this is essential. The segment inequality also uses a lower bound on Ricci curvature. But the important idea behind the segment inequality is you have a bulk integral that's small, and then you use that bulk integral that's small to actually get smallness along geodesics, which is what you need if you want to integrate along geodesics. Okay, but of course this can't possibly be true for like every geodesic. So it's only after you perturb the endpoints. Okay, I mean, one guiding principle behind why this can't come out too easily is we know for a fact that we're not going to get smooth convergence to Euclidean space. We're just not. So there has to be something that we have to play with. But the things that we play with always only involve moving distances a small amount, which is fine, right? Because we're proving Gromov-Hausdorff convergence, right? Not smooth convergence. So as long as we just move things a little bit, we're allowed to. Okay. So here's a picture that kind of illustrates the idea. So X and Y are not shown in the picture, but they're in those two little blue balls. So sorry if this is too small to see on your screen, but anyway, so I have 2 points X and Y, and I take a far away point QI. QI is far away in the like ith direction. Okay. Then what we can do is we can perturb those 3 points. So that's what the X star, Y star, QI star. So those are drawn in the picture. Okay. So that all of the Hessians of U1, U2, U3, that all those Hessians are controlled along all the geodesics that are drawn in the picture. So namely sigma, which connects X star up to QI star, and gamma sub S, which connects all the points of sigma S over to Y star. So in other words, again, so gamma S, those are all the green lines in the picture, and sigma is the other kind of wavy line that's going up, down. Okay, and then Z, we take Z to be the point on sigma that has the same value of U sub I that Y does. So on the pictures drawn sigma I of Y, that's the level set, that's the UI level set of Y. So the construction is I take an X, I take a Y, I perturb them a little, but then there's this Z, which you can think of as kind of like, it's this weird kind of projection-ish thing onto the level set of Y. Okay, but I'm doing this in such a way that I have smallness on all the geodesics that I've drawn on here. Okay. All right, so the next slide, I guess, is the most technical one, I suppose, but it's not too bad. So this is exactly what I mean when I say that. I said specifically, we're proving smallness for M of G sufficiently small, because remember, M of G controls the global L2 Hessian. So if M of G is sufficiently small, I can get this thing small, namely integrate over all those gamma curves of all the Hessians, that whole thing, just it's all small. Okay, I can get this to be as small as I want. So I can get this to be small, but also I can get this quantity to be small. So let me describe what this is. So this is an integral along sigma. Okay. And now sigma is the geodesic. So since I put the Q really far away, right, it's essentially pointing in the ith direction as when you get all the way up to QI. So the first term in this, I'm looking at the integral on the bottom. This first term here, right? I already know that gradient UI and sigma prime are very close to each other way up at QI. That's from my uniform asymptotics that I proved that we had. And then the second term, the sum, that's saying that the other U's, right? So remember, we're going in the ith direction. If you look at the grad UJ, so those are the other ones, those are nearly orthogonal to sigma prime way up near QI. So that little blue ball up near QI, we have really good control over the behavior of the gradients of U and the sigma prime, right? So then what we do is we take that and then we just use fundamental theorem of calculus along sigma to get control everywhere else along sigma. And the reason why that works is because, again, this geodesic does have the good property that the Hessians are, that the integral of the Hessians can be as small as we want. Okay, and so we just use fundamental theorem of calculus, and you can just see if you take this, right, what happens when you differentiate all the terms down here. Well, the sigma primes, if you differentiate them along sigma, they're 0 because it's a geodesic. And the gradient U's, that's the Hessian, which is small. So you can kind of fill in, vaguely fill in the details in your head that you can see. oh, well, those two terms are small, so I can show that they're small all along this integral, and that the whole integral is small from 0 to 0 from x star to z, I guess. Okay. All right, so I have one slide left to go, and so but I'm going to leave these equations behind. So maybe the second one, let's try to keep that in mind as I go to the next page, since I don't have it written again. Okay. So as in Cheeger holding, once we have this implies what they call an almost Pythagorean estimate, right? So the idea is because of the way that I've set this up, you can see that it satisfies some almost like the Pythagorean theorem. The distance from x to y squared equals the distance from x to z squared plus the distance from z to y squared. So remember, the distinction between x and x star is irrelevant because it's small in distance. So for the purpose of distance, this is okay. But also, we can see that the distance from x to z is specifically measured by the change in the u sub i's. Okay. Meanwhile, as you go from x to z, the uj's don't change much at all. And that's exactly, so maybe I'll go back. That's exactly what this thing is for at the bottom, why that smallness is important. Because that's saying that gradient ui is matching up with the geodesic. Well, then of course, distance is just measured by change in ui. And the fact that the grad UJs are orthogonal to the geodesic, that just tells you that the UJs aren't changing much as you go up the geodesic. So that's where this comes from. So if you combine what I have in the almost Pythagorean with this, where I actually tell you how the distances relate to the changes in U's. So the last step is, well, we do this 3 times. So basically, right, you project once to the level, to the I guess the U1 level set of y, and then you do it again to the U2 level set of y, and then you do it again to the U3 level set of y. So if you do this 3 times, right, then overall what it's going to tell you is that the distance from x to y is close to the Euclidean difference, right, between u of x and u of y, where this is a bold u and a bold, like the bold u is u1, u2, u3. That's the thing that we. So this is, I mean, there's a little more to it than this, but this is essentially what we wanted to show. We wanted to show that our distances are just like Euclidean distances, where the map to Euclidean space is explicitly this map u1, u2, u3. Okay. There's one more kind of technical, interesting point here actually, which is that a priori we do not know that the UIs even form a coordinate system. So like actually, if you project 3 times, you'll get to something that has the same U coordinates as Y, but that doesn't mean it's equal to Y. So there's actually a little extra step where we have to explain why after that projection process, you actually are at least close to Y. But I'll leave that. So I think that's pretty much all I wanted to say. So I guess I'll just wrap it up there. Unless it's the same from before.
No, it's a new question.
Great.
So the small, sorry, you're assuming the mass is small just to say that the L2 norms of the harmonic functions are going to 0?
Yeah, you need that just to
so this is, so you can view this as like an extension of the Cheeger-Colding theory, just saying that as long as you have these like n, and I guess you don't use 3 anywhere else, it's just you use n equals 3 to get the mass inequality.
Exactly, that's exactly right. So if we have that if that mass inequality were miraculously true in all dimensions, which for all I know it could be, then this proof would actually work in any dimension as well.
Okay, yeah, thanks.
Yeah, and yeah, a good point is right. So if you look at the Cheeger-Colding proof, I think the important thing is realizing that this essentially this like integral Hessian bound is kind of the hardest part of their proof, is getting that, and that's the one thing that we're getting for free.
Right.
So in some sense, it looks like things should work, but then we have to work harder for every other part of the proof. So it's kind of like a balance. But yeah, but like the of course the like there's some yeah, there's some amazingly good ideas in that work of Cheeger Paulding.
Okay.
I guess the Cheeger Paulding one, they also have just L2 on the
Sorry, I'm blanking. It could be L1, but it's not that different is the point, I guess. If you have L1 bound or L2, it's something I can't remember in their paper which it is.
Okay, well, thank you all for joining. I think we should maybe use Dan's talk as a model for clarity for the next few days. That was really excellent. So we'll see you all tomorrow.